Welcome back, everyone. This is Professor Herring. In this video, we're going to continue our exploration of chemical bonding. We're going to focus in this video on covalent bonds. We're going to talk about what is meant by the valence of an element. We're going to discuss bond dissociation energy and how we can use the bond order and relate it to the strength and length of bonds within different covalent compounds. Let's begin. To review, we've looked already at these three types of bonding in brief, but we're going to go into more detail about covalent bonding. To review, ionic bonding is when we have interactions of opposite charges, and that's found when metals and nonmetals interact with each other. The metal gives up its electron, and the nonmetal receives the electron. Within covalent bonding, these are bonds that are made up between mostly nonmetals, and they result in shared electrons. So the elements within water, the oxygen and the hydrogen, share them. We're going to go into more detail in a later video about whether or not they are shared equally, but what we need to understand right now is just that these elements are shared with each other. And with metallic bonding, these also have electrons that are shared between metals, but there's not enough electrons to fill the octet or the valence shells of all of the metals, and so they kind of slosh around back and forth between the metals. Let's dive a little bit deeper now into covalent bonding. As we've said already, covalent bonding is when the electrons are shared between the elements, between the nuclei, to form a molecule. Molecular compounds consist of individual molecules. In other words, there's a very distinct water molecule, and you could have it floating around another water molecule, but they are distinct and individual. And this is different from what we saw, whereas in ionic compounds, there's no individual molecule, but it's a continual lattice that stretches on for millions and millions of molecules. These are typically made up of nonmetals or metalloids, and some examples include hydrogen chloride, water, acetic acid, and ammonia. What happens in covalent molecules is that if we have two nuclei, the core electrons are held tightly to the nuclei, but the valence electrons are on the exterior and are able to circle around the nuclei within their orbitals. And so if we take a look at a very simple hydrogen-hydrogen system, we have one hydrogen atom and another hydrogen atom. The nuclei repel each other because of their positive charges, and the electrons repel each other because of their negative charges. But there's an attraction between the electron and the proton of the hydrogen atom, and that attraction is between the nucleus of an individual hydrogen and both electrons. And so we're not going to go into the complicated mathematics of it all, but what we can see is that there is a bonding region that's essentially in between the nuclei, and that has the highest probability of finding those two electrons. When those electrons are within the bonding region, that lowers the overall energy of our system, making the hydrogen-hydrogen bond a more favorable system than just two hydrogen atoms on their own. This is just reiterating what I just said about the bonding region being more stable than the isolated atoms. Something to understand about the properties of covalent compounds in general is that these have low melting or boiling points, and they can actually range from solid to liquid to gas at room temperature, and if they are solids at room temperature, they tend to be soft. Let's talk more about valence electrons. As I mentioned earlier, the valence electrons are the electrons that are involved in the bonding. And so if we take a look here at carbon and sulfur, we can see in yellow the valence electrons, and we can predict the number of valence electrons based on the main group number. Carbon is in the fourth group, and it has 4 valence electrons. Sulfur is in the 6th group, and it has 6 valence electrons. And so for main group elements, the number of valence electrons is equal to its group number. And we've seen already about the Lewis dot structures. We can represent carbon with 4 dots and sulfur with 6 dots. It is unimportant where those dots go in this Lewis dot structure. All it is an accounting function to be able to keep track of the number of valence electrons. The main group elements will tend to form bonds until they have completed octet. So in other words, if we have carbon, we know carbon has 4 valence electrons. And if it will form bonds with elements like hydrogen, each of which has 1 valence electron. They will share their electrons, and we can represent this either in the Lewis dot diagram or this Lewis structure with lines representing the covalent bonds. This structure will go much more into depth in Chapter 7, and you'll become very familiar with how to build them and how to represent them. And so what we see is that elements will tend to gain, lose, or share electrons so they can acquire an inert or noble gas configuration of the 8 valence electrons. Or, in the case of hydrogen and helium, they have a duet or a duo. They have 2 valence electrons in their outer shell. And so we can represent these molecules with a variety of valence or Lewis structures. Methane can be represented as carbon with a single bond to 4 different hydrogen atoms. Nitrogen, it has 5 valence electrons. It shares 3 of them to form NH3. And then water, oxygen has 6 valence electrons. It's going to share 2 of them with hydrogens to form water. And we see that there's a distinction. In 2 of these molecules, they have what we call lone pairs of electrons. And these don't participate in bonding. So what we do see here is that the Lewis structures show the connectivity of the atoms and the lone pairs and the locations of those shared electrons. In chapters 8 and 9, we're going to go much more into depth. In fact, 7, 8, and 9 will go much more into depth about Lewis structures, about how to draw them in 3 dimensions, and all the implications of what the structures mean in terms of their functions. But we want to get a basic idea for seeing Lewis structures right now. And one of the reasons for this is here on the following slide. And I'd like you right now to pause the video and look over these structures and see what patterns you can see in the bonding structures of carbon, hydrogen, oxygen, and nitrogen. Take 2 or 3 minutes to look over these examples and see if you can figure out some patterns. Welcome back. So hopefully you saw that in every case, carbon formed 4 bonds total. It could be 4 single bonds to the same element. It could be 4 single bonds but to different elements. We could form 2 single bonds and what's called a double bond. We could form what's called a triple bond with a single bond. But in every case it forms 4 bonds. Nitrogen, in every case, it formed 3 bonds. And as you can see, there's variation. It can form single bonds, it can form triple bonds. Not shown are double bonds, but it can form those as well. And oxygen, you'll notice, in every case is forming 2 bonds, whether it's a double bond or 2 single bonds. Nitrogen, oxygen, and then hydrogen is the last one here. You'll notice in every case, hydrogen is always forming a single bond. And we can summarize this in a rule that we're going to call the rules of valence. And we can summarize it in this way. The number of valence electrons in an atom determines how many bonds it will form. This we call the rules of valence. So when we look at the Lewis dot structure of the free atoms, we can see Hydrogen has one Lewis dot, it has one valence electron, no lone pairs, and it forms one bond. Carbon, nitrogen, oxygen, and the halogens have an increasing amount of valence electrons in their outer shell. Carbon is going to typically form 4 bonds. Nitrogen will form 3 bonds and 1 set of lone pair. Oxygen, 2 bonds and 1 set of lone pair. And halogens, 1 bond and 3 sets of lone pair. And again, what you're looking for is the number of valence electrons is going to dictate how many bonds it will form. So essentially, the number of bonds it will form is equal to 8 minus the number of valence electrons, or 2 in the case of hydrogen. Now, there are exceptions to this, but this is the general rule. And this is helpful, we will see later once we start looking at things called formal charge. So because carbon, nitrogen, oxygen, and some other elements are able to form multiple bonds, we need to discuss how that happens. It's all still through the sharing of electrons. And so a double bond is when we have 2 sets of electrons in between any 2 atoms. We represent that with two lines. A triple bond is when we have 3 sets of electrons that are shared between 2 atoms. And we represent that with 3 lines. We only ever see single, double, and triple bonds. Now, there are some elements that are going to form quadruple bonds, but that's well beyond the scope of Chem 110. And an important term here that you want to be familiar with is bond order. And this is the number of bonds between 2 atoms. So we always talk about between 2 atoms, not the whole molecule. That's a very common misconception that students have, is they will think that the bond order is the sum of all the bonds. And so the bond order here is 1. The bond order here is 1. The bond order between oxygen and carbon is 2. And the bond order between the nitrogens is 3. As we saw already, we can form different combinations of single, double, and triple bonds. Carbon always forms 4 bonds, and it can be in any of these combinations. Nitrogen can form 3 bonds in any of these combinations, and oxygen forms 2 bonds in any of these combinations. And what we see is that these rules would apply to other elements in the same group. In other words, nitrogen is just above phosphorus on the periodic table, and phosphorus tends to form 3 bonds. Oxygen is above sulfur on the periodic table, and sulfur tends to form 2 bonds. Just below nitrogen is silicon, and it turns out that silicon is too large to form multiple bonds. And in fact, beyond phosphorus and beyond sulfur, we have arsenic and selenium, and these tend to misbehave, if you will. They're not going to follow the same rules. And so what we see is that these rules of valence apply best to our smaller elements on the first couple rows of the periodic table. We need to understand that there's a relationship between the bond order and the strength and length of a bond. The bond length is the distance between the two nuclei when those elements are bound together. And we can, if we break those bonds, we call that the bond dissociation energy. And it's important to know that this is only between covalent bonds. So this is distinct from lattice energy, where the lattice energy told us about the energy required to break ionic bonds. Bond dissociation energy describes the energy required to break covalent bonds. In this case, we've already talked about bond order. And when you take a look at the measurable values for bond length, what we see is that there's an inverse relationship. That is, the bond order increases, the bond length decreases. We'll talk more about why this happens once we get into a couple of chapters down the road. But suffice it to know that the longer the bond, the weaker it is. And we see this here. The bond dissociation energies are inversely related, are directly related to bond order and inversely related to bond length. So the nitrogen-nitrogen triple bond is much, much stronger than the double bond, which is much, much stronger than the single bond. And the way you can think about this is like, let's say that you have rope that you've tied between you and your friend are holding onto a rope. And if you take the rope and you fold it over on its ends, let's draw a little diagram here. You and your friend have a rope between you. And if you try and pull on it to break it, you're going to exert some energy to break it. But if you take that rope now and then you fold it over on itself, and you loop it back, those increased folds are going to make it tougher to break because there's more material holding it together between the two of you. And so this is going to be easier to break, and this is going to be harder to break. The final thing that we need to talk about in this video is polyatomic ions. And polyatomic ions you are expected to be familiar with already from high school chemistry. If you're not, then you need to go and you need to look them up in table 661, and there's explanations throughout there, some links to various other pages that talk about how to name the polyatomic ions and other monoatomic ions. And so if you don't know how to name the ions, and if you're not sure of the names of them, then you need to spend some extra time looking them up and memorizing them and coming to understand them, because it will be expected that you can use them easily on celebrations of knowledge and other activities. So polyatomic ions, if you notice, for any given ion, it's made up of nonmetals, with a few exceptions. So they're mostly made up of nonmetals, and therefore they have covalent bonds between the elements within the ion. However, because they're all charged, when they combine with other cations, in the case of the polyatomic anions, or when they combine with anions, in the case of the polyatomic cations, they're going to form ionic compounds. So something like sodium hydroxide. This is a polyatomic ion. Therefore, it has covalent bonding. Because we have a metal with a nonmetal, we then get ionic bonding as well. And so sodium hydroxide exhibits both ionic and covalent bonding. Additionally, it's going to have, while it does exhibit both, this is an ionic compound. Therefore, it behaves similar to ionic compounds, where they have high melting or boiling points. They're very brittle. And so while there is covalent bonding present within these molecules or compounds, it is an ionic compound, and it behaves similarly to an ionic compound. That's it for this video today. Thanks for watching. If you have questions, be sure to ask on Piazza, in office hours, or in recitation. Have a good day.